This is Lab 5, measurement of spherical aberration. I'm Nathan Isham.
I'm Stephanie.
I'm Al, yeah. So in this lab, we focus on the spherical aberration.
Get it? Focus?
So in this lab, we focus on the spherical aberration. And ideally, in an optical system, all the rays should focus at the paraxial focus. But if the spherical aberration is present, the ray that hits the edge of the lens will focus at the marginal focus instead. And the distance in between will be the longitudinal aberration. And the transverse aberration will be the transverse ray error from top of the pupil. And that equation gives the coefficient of the spherical aberration. And even by optimizing the shape factor and conjugate factor, there is no way to minimize the spherical aberration to 0 due to these terms here. So we also determine the ray fin errors, and they are the functions of normalized pupil coordinates. So an image plane can be shifted away from paraxial focus to obtain better image quality. So one way to compensate spherical aberration is to add defocus. So as you can see at the marginal focus, the RMS ray error is reduced, and it can be further minimized when you place the image plane at the mid focus.
This week our setup looked a little bit different than it normally does. We had to set up our laser so that it was perpendicular to our normal optical rail. This was because we had to put in a pentaprism so that we could scan a beam across the lens. But before the lens, we ran it through this Hartman filter. We use this to find various elements of the system, in this case, marginal focus. So we started out by sending the beam through the central hole of the Hartman mask and aligning the beam so that it was on the center of the screen at the end of the rail. We then moved the beam across the Hartman mask until it was at one of the extreme ends, and then to find the marginal focus, we moved our microscope along the axis until the spot on the screen was centered again. This point was defined as marginal focus. Right now we are at marginal focus on our Hartman mask. As we start to scan, you'll see that we will have these vertical fringes, and this is due to the beam being a larger size than the space between the apertures. So you have a double slit type experiment going on between that, and as you go to the center of the holes, you will also get circular fringes, and this is due to the fact that the beam overfills the aperture, so we are getting diffraction effects off the edges, causing the circular fringes that we see around the center of the beam. You can see as we scan across the Hartman mask, we have a slow motion of the center of the beam to the right. This is because of aberrations due to the lens.
So we're able to find our transverse ray aberrations by adjusting the location of the prism. We moved this axially to the laser, and this shifted the beam position on our Hartman mask. So we did this for translated the prism through each of the holes, and respectively we also adjusted the microscope to bring its beam position back to its original location. We recorded these change in positions, and we're able to plot our data from this. So these are our ray aberrations for our on-axis ray. We were able to calculate these for their different shape factors, b=1, which was the convex side facing the laser, and b=1, which was the plano side facing the laser. We were able to obtain this data by normalizing our microscope reading and our prism location. We normalized our microscope reading by referencing on the Hartman mask from our actual position to the central hole. And we can see that we had more aberration for our shape factor of -1, which is kind of what we had predicted in our pre-lab. We were also able to calculate our longitudinal ray aberration for our shape factor of +1, and this is what we got.